Hello viewers of mine, this is a What the Physics video. This one is on energy, work, and energy conservation. Specifically, this one is actually going to be on a focus on work. But yeah, I just want to get people excited about the energy. Kind of boost up the energy for energy. Whoa, it's like a meta thing. All right, here are the work learning targets. I can identify when work is and is not done on an object. And I can calculate the work done on an object, the power exerted, and relate these values to change in energy. Oh yeah. Woo! So, working hard or hardly working, right? Oh, it's a dad joke. You gotta love those. You just do. Or you just gotta tolerate them. Sorry. So, I bring this up because, hey, we've all heard the term work before. We use it all the time outside of physics class. What we've got to do is be careful that we don't mix up the physics definition with the non-physics definition. So non-physics uses of the term work could be including, oh, I got to do homework, I got to do classwork, yard work, housework, I've got to go to work. I've got to work out. All these things make sense outside of physics, but you know what? They may not actually be considered work in terms of physics. So let's go ahead and define physics version of work. Okay, this is the product of the forces exerted on an object and the displacement the object moves in that direction, or W equals FD. And we'll clarify what that equation is in just a moment with a little extra bits. But one of the big things here is if the direction of the exerted force is at 90 degrees from the direction of the displacement traveled, no work is done. You say, what? That's so weird. Yeah, the force and the displacement have to be at least somewhat in the same direction or somewhat opposite direction. Okay. And to keep all this in mind, we're going to add to the equation a little bit. It's going to be work is force times displacement times cosine theta. Because folks, you know that cosine of 90 degrees is 0. So if I go ahead and do a huge amount of force with a huge amount of displacement, but they're perpendicular to each other, in other words, 90 degrees, I didn't do any work. What? I know. But if I do this huge force and huge displacement, and the force and displacement are parallel to each other, in other words, the angle is 0 degrees, hey, what's the cosine of 0 degrees? 1. It's positive 1. Ah, yay. Okay, and BT dubs, the units for work are joules, which is capital J. You can also use Newton meters, whichever. Joules, Newton meters. Oh yeah. All right, work it, baby. Oh, no, let's not. No. Okay, the most difficult aspect of doing work is figuring out if you're doing work or not. And let's clarify what that means. If we're moving in the x direction, only the x component of the force is going to be counting. And that's assuming we're accelerating in the x direction. So let's say I'm pulling my wagon. Pull. Notice whenever you're pulling a wagon or a sled or whatever, it's typically at some type of angle. But my displacement is this away here. So what I'm going to do is I'm going to figure out about the force component that is parallel to the displacement. That is going to be, in this case, the x component of that force. So what I'll do is I'll multiply the x component of the force, or in other words, force times cosine theta, times the displacement. And that will be my work. So that means, yes, work is done. Whew. Yes. If you push on something, but that something doesn't actually move, no work is done. So if you're pushing on a brick wall, got a lot of force that you're exerting on the brick wall, but because there's no displacement, there's no work done. So unless you're like the Kool-Aid guy, like, oh yeah, just busting through the wall, yeah, no work is done. How about this? You are moving, but you're moving horizontally to the side. You got a displacement to the right maybe, and your force is upwards. Oh, there's that whole 90 degrees thing. Oh, yeah, no work is done. Say what? So, what is work? Well, we already have the whole equation, force times displacement times cosine theta. But think of it this way. By doing work on an object, you are giving that object energy. You say, oh yeah, I remember learning about energy already. You can think of energy as the ability to change itself, the object itself, or change the object's surroundings. You can also think of work as the transfer of energy by mechanical means. Okay, so there's me working out. Ugh. See, I'm wearing my tie. Okay, so I'm lifting upwards, I'm doing positive work. But then as I'm putting it back downwards, I'm actually doing negative work. Huh, that's weird. You see, lifting a box is going to mean a transfer of energy from you to the box. You do work on a box, you are giving the object, the box, some energy. If you do positive work. If you do negative work, you're actually taking away energy from the box. We'll go into more detail. So anyhow, you are doing work on the box. Now the box has more energy. So lifting up, well, that's not how you should lift. But lifting up that box, you're giving the box more energy. Lowering the box transfers energy from the box to you. So that is negative work. Negative work is being done. Or the box is doing work on you. You can kind of think of it that way. Anyhow, the box now has less gravitational potential energy. Okay, so work is the change in energy. If it's positive work, that means an increase in energy. If it's negative work, that's a decrease in energy. And this can be kinetic energy, can be gravitational potential energy, and it can be spring potential energy, all those. Okay, so that's work. What about power? When I think of power, what do I think of? See, this is the nice thing about power. In the case of work, it's a little bit confusing, like, oh, does this actually count as work? Because I normally think of work as da-da-da-da. Okay, with power, when you think of something powerful, like me, no, never mind. That is going along with the physics definition of power too. So think of this car peeling out, right? Right? Lots of power. This is a demonstration I would love to be able to do in physics class, but I'm not sure if we're actually allowed to, but I think it'd be really cool if we could measure the power from pedaling and then like try to light a light bulb and stuff. That'd be neat. Okay. And of course, his power level is over 9,000. Indeed. So what in the world are we talking about? Power is the rate at which you do work, which is also the rate that energy is transferred. So power is a rate. Power is a rate. Work doesn't pay any attention to how long it takes to do something. Work does not care about time at all. Whether you walk slowly up the stairs or you run up the stairs, it's the same amount of work. But power, that's going to be different. So power is work divided by time. So if you take a very short amount of time to do something, that's a very small denominator, same work, big power. If you take a long time to do something, that's a big denominator, same work. That's going to be a small overall number. That's a small amount of power. Okay, so power is work divided by time, or you can say it's a change in energy divided by time. You can also say this, it's force, oh, you know what, that's wrong. That's not right. It should be force times velocity. Oh, I know what I did. I copied and pasted from earlier. Make that a V, please. Force times velocity times cosine theta. Make that a V. Velocity, velocity, velocity. Sorry about that. Oh well. Units are watts, capital W, where 1 watt is 1 joule per second. And you say, wait a minute. I thought W was work. Yeah. Yeah, that's kind of awkward. And I kind of wish we had more letters to be using in here, but we don't. So yeah, W, when it's a concept, like a variable, that is going to be work. When W is a unit, that's going to be watts. We just have to be very careful. Let's see. So let's say it takes me 2 seconds to lift a 5 Newton box 3 meters. That means the work I've done is 15 joules because force times displacement. 5 times 3, and then newtons times meters. 15 joules or 15 Newton meters. So if it takes me 2 seconds to do that, that is going to be a rate of 7.5 watts. 7.5 watts, or you could say 7.5 joules per second if you would like. That's fine too. Now, what if you were to do the same task, same box, same displacement, but in only 1 second? How is that going to change things? Well, it's not going to change the work at all because work doesn't pay any attention to time. It's still 15 joules. But what's the power going to be? Well, it's 15 watts. You say, wait, is it the same thing? Wait. Well, yeah, 15 joules divided by 1 second. I said I'd do it in 1 second, so that's going to be 15 watts. Okay? Don't forget to change that to a V. Force times V cosine theta. It comes from saying D divided by T. Yeah. All right. Then I want you to try this out. Am I doing work? Explain why or why not for each, and then include a force displacement or FD sketch. So go ahead and go through this and then go through some wonderful example problems. It's going to be awesome.